Module 2, Power Generation Systems and Cycles. 2.1 Steam Power Plants and Cycles. Steam power plants are among the most widely used methods of generating electricity. Their heart lies in the steam cycle, where water is heated, converted to steam, expanded through turbines, and then condensed back into water. Key cycles. Carnot cycle, the theoretical ideal. Rankine cycle, the practical steam cycle used in real plants. It introduces condensation and pumping to make the process feasible. Superheat and supercritical cycles improve efficiency by raising the steam temperature and pressure. Hans cycle, a modification of Rankine, incorporating real-world efficiencies. Regenerative cycles use extracted steam to preheat feedwater, improving efficiency. Reheat cycles reheat steam after partial expansion to reduce turbine moisture and increase work output. 2.2 Steam turbines and their design. Turbines are the core of steam power plants. Condensation of steam. After expansion, steam is condensed in condensers to maintain efficiency. Multi-stage turbines split expansion across several stages to reduce losses. Impulse turbines, steam jets strike blades, imparting force. Reaction turbines, steam expands within the blades, producing reaction forces. Multiple casing turbines distribute expansion across several housings to handle very high pressures. Non-condensable fluid turbines, used for working fluids other than water. Regulation and control. Steam control devices adjust flow for load changes. Power regulation methods include total admission, partial injection, and sliding pressure. 2.3 Gas power cycles. Gas turbines are widely used for aviation, electricity generation, and mechanical drive systems. Ideal gas cycle, modeled by the Brayton cycle. Real gas cycle includes losses and inefficiencies. Key performance factors include turbine inlet temperature, pressure ratio, and component efficiencies. Enhancements. Regeneration, using exhaust heat to preheat compressed air. Intercooling, splitting compression into stages with cooling in between. Reheating, expanding in multiple turbine stages with reheating between. These methods increase efficiency and reduce fuel consumption. 2.4 Combined gas-vapor power cycles. Combined cycles link gas turbines with steam turbines. Hot exhaust gases from the gas turbine generate steam for a secondary steam cycle, greatly improving efficiency. Operation principle: gas turbine exhaust passes through a recovery boiler, producing steam for a steam turbine. Thermodynamic advantage: utilizes waste heat that would otherwise be lost. Performance: combined cycles achieve efficiencies above 60% under ideal conditions. 2.5 Internal combustion engines. Internal combustion engines remain central to transport and small-scale power generation. Sliding crank mechanism converts piston motion into rotary motion. Lennox cycle, an early form of internal combustion cycle. Otto cycle represents spark ignition engines, such as petrol engines. Diesel cycle represents compression ignition engines, where fuel is injected into high-temperature compressed air. Efficiency comparison. Otto engines are lighter and faster but less fuel efficient. Diesel engines are more efficient and durable but heavier and costlier. Performance depends on compression ratio, speed, fuel type, and load conditions. In this module, we explored practical systems of power generation. We studied steam power plants, their cycles, and turbines. We examined gas turbines and methods to improve their efficiency. We considered combined gas-vapor cycles, which represent modern high-efficiency plants, and internal combustion engines, vital for mobility and small-scale generation. Course conclusion. We have now completed the course Energy Conversion and Power Generation. Module 1 gave us the foundations: global energy outlook, forms of energy, turbomachinery, economics and environment, load curves, heat transfer, thermodynamics, and fluid mechanics. Module 2 applied these principles to power generation technologies, steam power plants, gas turbines, combined cycles, and internal combustion engines. The key lesson is that energy conversion lies at the intersection of science, engineering, economics, and sustainability. As energy demand continues to grow, engineers must design systems that are efficient, reliable, and environmentally responsible.